When a polynomial function is written in factored form, it makes it really easy for us to identify what the zeros are. Because when we look at an example like the one that we have here, as long as it's written in this factored form, we know from experience that we can take each of those individual factors and set it equal to 0, and then solve to find the places where the graph is going to cross through the x-axis. So this is a good step for us if we're trying to build the graph of a polynomial function. So again, it says here, as long as we know some number is a 0, then we know that x minus that number is a factor. So in the case of the first example here, if we want to find the zeros of this polynomial function, I'm just going to take each one of these factors, set them equal to 0, and then solve. So here, if I add 4 to both sides, we get x equals 4. If I subtract 3 from both sides in the second example, I get x equals negative 3. And if I add 1 to both sides of the last one, I get x equals 1. So taken all together, we've got x equals 4, negative 3, and 1 are the zeros of this polynomial function. And so then with that information, if we were asked to, we could then start to piece together our graph. So we could go to 4, I'm just going to estimate it here, 1, and then negative 3, and those would be the places that our graph would cross through the x-axis. And then if we look at what this would result in if we were to multiply it all out, we're not going to have to do that, but if we did, we can see that we would end up with x cubed as one of our terms. If we were to eventually FOIL everything out, we would end up with 1x cubed as the first highest exponent term. And so then using our leading coefficient test, that would tell us that we have a disco graph, meaning one side's going to be up and one side's going to be down. And we also know that it's going to be up on the right and down on the left because the coefficient in front of that x cubed would turn out to be positive. And so then that means that I know that after we cross through the x-axis the last time, my graph is going to be going up on the right, and the same thing on the left, but going down. The last time we cross through the x-axis, we're going to be going down forever. And so then in between, we know that we're going to have some sort of movement like this, where we're going to dip down below the x-axis, come back up, and then cross back down. But if all we're asked for is to find the zeros, then we can get to here, and we're in good shape. If we move on to the second example, same idea. It's written in this factored form, so I have 1, 2, 3, 4 separate factors. We don't want to overlook the x that's out front there. That's one of our factors here as well. So we've got to set each of these equal to 0. So x equals 0 takes care of itself. X plus 2 equals 0. X minus 9 equals 0. And x plus 5 equals 0. So if we subtract 2 in this second one, we end up with x equals negative 2. If we add 9 on that factor there, we're going to get x equals 9. And then finally, if we subtract 5 from both sides, we'll get x equals negative 5. So taken all together, we've got 4 zeros on this one, so we can list them off. And I'll go in numerical order this time. Negative 5, negative 2, 0, and 9. So those are our zeros. And if we do the same thing that we did on the other one, what would this translate to on a graph? So again, just kind of working on it in a rough manner, we've got zeros at roughly negative 5, let's say here, negative 2, 0, and then 9. So we've got these 4 zeros. Now again, if we were to FOIL all of this out, we can tell that we're going to end up with x to the 4th as our highest exponent. And there's nothing that would cause that x to the 4th to be negative, so the coefficient would just end up being 1. So what that tells us is that we have a touchdown graph. It's going to go up to infinity on both sides. And because this leading coefficient would turn out to be positive, it would be going up rather than down. For a touchdown graph, it's either both sides up or both sides down. So in this case, it would be both sides up. So we know on the left, the last time we cross through the x-axis, the graph is going to shoot up to positive infinity. And the same thing is true, over here on the right. And so then in between, we're just going to be dipping down above and below the x-axis in a smooth manner. We don't know exactly how far down or how far up we're going to go. That's not too important here. We just want to get like a rough idea of what the graph looks like. So something like this is what we're going to end up seeing. And so to generate that graph, we could use a graphing calculator or Desmos, and we'll be doing that later on in future sections. And the last two examples here, we're basically working backwards from what we saw in the previous couple of problems. So here we're now given the zeros of a polynomial function, and we want to work backwards to write it in that factored form, and then eventually multiply that out to end up with our polynomial function in standard form. So recall that whenever we have an irrational zero, so something like this root 6, they always come in conjugate pairs, plus minus pairs, so that means negative root 6 is also going to be a zero of this polynomial function. It's just the nature of these types of zeros. They always come in these opposite plus minus pairs. So if we wanted to write the equation for this function to start off in factored form, well, we can say x minus root 6. It's always x minus whatever the 0 is. And then I'm going to use this one next. X minus negative root 6 becomes x plus root 6. And then finally, x minus 2. So those are my three factors. So even though there are only two listed, this one is implied based on the nature of these irrational zeros. So if we then FOIL this out to get it from this factored form to our regular form, standard form, I'm going to use a little FOIL, and this is where using some strategic planning comes in place. We definitely want to multiply the plus and minus root x pieces. It's going to make our life a lot easier because we have a difference of squares pattern. So I'm going to multiply x times x. I'm going to get x squared, and then I can skip the outer and inner pieces and just multiply the lasts, since those outer and inner pieces are going to cancel each other out. So I've got negative root 6 times positive root 6. So it's going to give me a negative, and then root 6 times root 6 is just 6. So we get a nice simple answer here. All of our square roots are now gone. That's why we want to approach it this way, is multiply those first. So then I can go ahead and FOIL one more time. So I'm going to multiply x squared times x and get x cubed. I'll multiply my outer. X squared times negative 2 is negative 2x squared. The inner, negative 6 times x is negative 6x. And then my last, negative 6 times negative 2 is positive 12. So we've taken our zeros, written them as factors, and then we've taken those factors and FOILed them out to end up with our polynomial function in standard form. For the last one, this time we have a regular integer as a 0, and then we have this complex 0, so 2 minus I. And just like with the irrational numbers, recall that these also show up in conjugate pairs. So our other 0 that goes along with 2 minus I is 2 plus I. So in these zeros that have both a real and an imaginary part, the 2 minus I, the real part stays the same, and the imaginary part changes to its opposite. So we have 2 minus I, so that means 2 plus I is also going to be a 0. So this creates a pretty complicated circumstance for us to have to FOIL through, but we'll get there. So we have f of x equals, I'm going to do the same thing as I did before. I'm going to write x minus 3 as my first factor, since 3 is a 0. And then for these next two, it's x minus, and then in parentheses, I need to put 2 minus I, and then my other factor is going to be x minus, and then in parentheses, I need to put 2 plus I. And I need this extra set of parentheses because this negative is going to end up being distributed to all parts of that particular 0. Same thing is going to be true over here. And so that's going to be the first thing that I'm going to do here before I start FOILing anything. I'm going to distribute those subtractions, those negatives. So this is going to end up with x minus 2 and then plus I, and then it's going to be x minus 2, and then if I distribute again, minus I. So now I'm set up to be able to do my full FOIL. And so again, we definitely want to start by FOILing these last two pieces that involve the imaginary units, because if we FOIL those first, even though it's going to be a lot of pieces, we're going to find that all of our i's are going to cancel out and disappear. So I'm going to keep that x minus 3 separate, and so now I just need to make sure that everything from this set of parentheses here multiplies everything in the second set of parentheses. I just have to be systematic about it. So I'm going to take x times x, and I'm going to get x squared. Then I'm going to take that x and multiply it by -2, and then I get -2x. And then I have to take that x and multiply it times that -I, so I get -xi. Now I need to go through and do the same thing for the -2 that's right here. That needs to be distributed to everything. So -2 times x is -2x. -2 times -2 is +4. And then -2 times -I gives me +2i. So now I just have one more round of distributing. It's this I here that has to multiply everything. So I'm going to get a plus xi or ix, doesn't matter on the order. I'm going to get a -2i. And then lastly, +i times -I gives me -I squared. So pretty long involved expression there, but hopefully we can see that there's quite a bit of like terms and quite a bit of canceling out that's going to happen. So I still have this x minus 3 here. So now as I start to clean up this long expression, I've got x squared. Now, -xi has a positive xi here, so those are going to cancel out. I've got a positive 2i and a -2i, so those can go. And then don't forget that this I squared right here is -1. So I have minus -1, so that becomes +1. I can go ahead and make that change. So now as I continue to gather up the rest of my like terms, I have a -2x and another -2x, so that makes -4x. And then I have this +4 and this +1 gives me +5, and everything else involving the i's has canceled out. So that's why we want to multiply those factors that have the i's in them first, because if we do that, then all of our imaginary pieces will be gone, and now we just have a more standard FOIL left to do. So we've got to multiply these two pieces. So again, I'm just going to take everything from the first set of parentheses, make sure it multiplies everything in the second. So I've got x times x gives me x cubed. X times -4x is -4x squared. X times 5 is 5x. And then I'm going to do the same thing with the -3. I get a -3x squared. I get -3 times -4x is +12x. Make sure that looks like a +12x. And then finally, -3 times 5 is -15. So our last, have a straight parenthesis there. So our last thing is to gather like terms one last time. So I'm going to start with the highest exponent. I just have x cubed. I've got a -4x squared and a -3x squared. Gives me -7x squared. I've got a 5x. Remember, this was a +12x. So that gives me 17x. And then lastly, I've got that -15. So after a long and winding road, we've ended up with our polynomial function.